This is question number 62 in chapter 7. It reads a 0.145 kilogram baseball is pitched horizontally at 35 meters per second, and it strikes a bat as popped straight up to a height of 55.6 meters. If the contact time is 1.4 milliseconds, calculate the average force on the ball during contact. I've made a sketch of what's going on in this problem. The baseball is initially pitched at 35 meters per second. It comes in, it strikes the bat. We can see it striking the barrel of the bat here. We know that right before it strikes the barrel of the bat, it's doing 35 meters per second. Right after it strikes the barrel of the bat, we have no idea. I'm calling that position 2 here. We don't know how fast it's moving. And then it eventually gets 55.6 meters above the bat head, where it reaches its maximum height. I'm calling that position 3. So we're really just focused on what's happening when the ball strikes the bat. Its initial velocity before the bat and just after striking the bat, which we're calling V sub 2. We're eventually going to have to find that. Conceptually, when I look at this problem, I should immediately be thinking to myself that this is an impulse momentum problem. How do we know that? Well, first of all, we're talking about time in the problem, and they're asking you about average force. And the mass of the ball is given, and we can see that there's a whole bunch of delta V's going on here. So it's got all of the trappings of an impulse momentum problem. So I'm going to go ahead and write that out. It's going to be force times time is equal to final momentum minus initial momentum. It's also important to see that momentum is changing in two different planes here. It's changing in the x plane and the y plane. So initially, the ball has a velocity going to the right and a momentum going to the right in the x direction, and then its final momentum is 0. That means that, technically speaking, its change in momentum is to the left. And we'll also see that in the y direction, it experiences a change in momentum. It's initially 0, not going at all in the y direction, and then it's going in the upwards direction. So we can see that the change in momentum in the y direction is up. I'm going to go ahead and label both of these. So I've got my change in momentum y is up, and I've got a change in momentum x acting to the left. Of course, we're going to end up adding these two vectors together using the head to tail method. And so I can go ahead and do that here if I wanted to. Now I'm moving the y momentum component so that it's arranged at the tail of the x component, and then I can see that the resultant, or the net change in momentum here, can be described by that ray connecting the beginning of the first momentum vector, in this case the x component, and the end of the second one. So let me go ahead and label that delta p, and I'm just going to call that maybe the resultant, or perhaps the sum of the x and the y pieces. Whatever I want to call it is completely fine. So I'm going to leave this sketch here so that I can reference it later on in the problem. It's immediately apparent that I'm going to need v sub 2, the velocity of the ball after it's been hit. So there are a variety of ways to kind of solve for that. We do know some kinematics information here. We know that the acceleration of the ball is negative 9.8 meters per second. Or you can use conservation of energy methods to do the same thing and say that the kinetic energy of the ball, just as it's leaving the bat head going up here, must be equal to the gravitational potential energy of the ball when it reaches its maximum height, if we call that reference plane at the bat 0. I'm going to use that method. So step number 1 will be to solve for v sub 2. Step 1, solving for v sub 2. All right, again, using conservation of energy methods, the sum of mechanical energy at position 2 must be the sum of mechanical energies at position 3. In this case, I've only got kinetic energy at position 2, and I've only got gravitational potential energy at position 3. That leaves me with 1/2 mv squared at point 2 must be equal to the mgh at position 3. I'll see that the masses cancel out here. I do have the mass of the ball, but I ultimately don't need it, at least for this part of the problem. And then I can say that v sub 2 is going to be equal to the square root of 2g h sub 3, where g is 9.8. So now I can say that v sub 2 is equal to the root of 2 times 9.8 meters per second times the height given to me in the problem as 55.6 meters. I'm going to go ahead and extend that radical sign here, and then I get v sub 2 is equal to 33 meters per second, and of course that's in the upwards direction here just after it's being hit. So now I know how fast the ball is going when at the moment after it's hit the bat. So now I'm going to go ahead and in the next part of the problem solve for the change in momentum in both the x and the y direction. Let's go ahead and start in the x direction over here. So in the x direction, I'm going to say that impulse, force times time, is equal to the final momentum minus the initial momentum. And another way of writing that out is force times, or force in the x direction times time, is equal to m, or mass of the baseball, times the final velocity minus the initial velocity. I like this form right here because I think it's going to be easiest for me to kind of pay attention to as I solve the rest of this problem. So I think this one here is the one that you should be focusing on. So in the next step now, I can solve for the average force in the x direction. The average force in the x direction is going to be equal to the mass of the baseball, 0.145 kilograms, times the final velocity, and this is in the x direction. The final velocity in the x direction is, of course, 0 meters per second, because after it gets hit by the bat, it's only going straight up, minus the initial velocity in the x direction, which is going to be 35 meters per second. And, of course, I need to divide all of that by the time. And so that's going to be 0.0014 seconds, which is the equivalent in seconds of 1.4 milliseconds. When I run that through my calculator, I end up getting 36,000 newtons. And it's also important to recognize that that is going to be negative because it's to the left, which is what I'm expecting. I expect the force on the bat to be in the x direction, pushing to the left. All right, let's go ahead and now do the same thing, except we're going to do it in the y direction. So in the y direction, I can say that Ft, and I'm going to stick with that this form here for the impulse momentum equation. F in the y direction times time is going to be equal to the mass of the baseball times v final in the y direction minus v initial in the y direction. Okay, so solving for f sub y, I'm going to get something that looks similar, except the mass of the ball, of course, doesn't change, 0.154 kg. But then I need to put in the final velocity in the y direction. The final velocity in the y direction is going to be 33 meters per second. Remember, this is in reference to contact with the bat. So it's going to be 33 meters per second going up, which makes it positive, minus the initial velocity in the y direction, which is 0 because it's not moving in the up direction, in the y direction initially. And then again, I divide that all by the time of contact, 0.0014 seconds. Now that I run that through my calculator, I get 3,400 newtons in the y direction. And I've just caught a mistake now that I've made in that section above. Clearly, this is so small compared to that. I reran those numbers and realized that I had an extra 0 here. That's 3,600 newtons, not 36,000. That becomes negative 3,600 newtons. Sorry about that. Okay, so now I have my x and y directions, and so per usual, I have basically two sides now of my triangle. I have this piece, my y component, and my x component, and I can use the Pythagorean theorem now to find my resultant. So I'll go ahead and do that. So I'll say that my resultant force in this case, I was drawing circles around the y components, but ultimately these would be the same diagram for the force. So the resultant force can be found via the Pythagorean theorem. The resultant force squared is going to be the x component squared plus the y component squared. Therefore, the resultant force F sub r is going to be equal to the square root of the x component squared, which is now negative 3,600 newtons. I got to remember to square that. and to it I'm going to add 3,400 newtons. Got to remember to square that. And when I do that, I get about 5,000 newtons. So the magnitude of my resultant is 5,000 newtons. I'm not quite done yet because I still need to pay attention to that angle theta. So force, of course, is a vector and therefore requires an angle, a direction, as well as magnitude. So since I know the f and the y piece, by the way, again, one more time, you know what? I'm just going to sketch this over here just to kind of make the point. So if this is my coordinate axis, my x component force acts to the left, my y component force acts up, and therefore my resultant force is going to be here. You can use the head to tail method or the parallelogram method, whatever graphical method you feel like using to kind of illustrate this. I prefer the head to tail method here. Constructs that nice right triangle. You can see that they're totally related to what's happening in the momentum vectors as well. Let me go ahead and label those just for clarity. F sub x, f sub y, f sub x here, and this is going to be my resultant, f sub r. Okay, so now I'm looking for this angle theta. The trigonometric function that relates y to x in this case is going to be tangent, so I'm going to get tan theta is equal to opposite over adjacent. This is the TOA and SOHCAHTOA. And in this case, the opposite side of that is f sub y, and the adjacent side is f sub x. And then I'll take the inverse tangent of both sides. So basically, my next step leaves me with theta is equal to the inverse tangent, or the arctan, of fy over x fx, which in this case is going to be 3,400 over negative 3,600. And you have to be careful with what your calculator is going to spit out here. It's going to be confused as to what quadrant you're in, but I need to recognize that if I'm referencing the negative x-axis here, that's going to be 43 degrees. If I want to, I could subtract that from 180 if I was, really wanted to reference the positive x-axis. But in this case, the magnitude is 5,000 newtons, which is part of my answer, and the direction is 43 degrees.